Hello everyone, my name is Ludovic Taguema. I'm a research engineer at Cenaero, and today I'm going to present you two investigations of innovative compressor blade design using SU2 that were part of some preliminary studies we did at Cenaero before tackling LES simulation, high order simulation. For us, it's important to better understand the flow field and the characteristic of this um, innovative compressor before getting head on with the LES. So the first case is a compressor tandem blade cascade, and it has a fairly usual configuration. So it's a front blade. Okay, there's a front blade, a rear blade. The total axial chord is one of the important parameters, and we define the domain actually with an inlet where we set the total pressure, total temperature, and a Mach number and an angle of attack. At the outlet, we set the static pressure, and we have a pitchwise periodic condition. And the idea is to be able to better understand the flow field in this configuration and see if we happen to not have boundary layer separation that we might observe if we were simulating a blade of a similar axial chord, but in only one composition. So we assume the flow to be air with an inlet Mach number of Mach equals 0.6, a Reynolds number based on the total axial chord, and the inlet condition of 550,000 and a turbulent intensity of 5%. Simulation is steady runs with the SST model, and for the numerics we compute the gradient with the weighted least square, and the convective scheme we use is the GST. And we perform quite an mesh study to be sure that our quantities will be fine enough. So we make sure that the Y plus is mostly below 1 to be sure that the boundary layer and the effect that we will see for the turbulence model will be correctly represented. And we obtain that's a flow field that here represents the Mach number. And as we can see, we have a boundary layer that is attached on both blades. So we do not observe any separation, which enables us to have a higher term with lower losses than if we were having only one given blade that were not separated. Moreover, the wake of the second blade is constraining the flow above the first blade is constraining the flow above the second one, and it accelerates it, and then it mixes in the wake region. And for this domain, we realize that for different inlet angle of attack, we find a minimum of losses at the operating point that we want for this cascade, and which is at 50 degree. But if we move away from this operating point, we observe losses. However, due to the nature of this configuration, we win 1 degree of freedom. And in this study, we made variation of the stagger angle rotating around the trailing edge. We also did 2 other studies where we're rotating around the midchord and outside rotation center. And the goal is to be able to find stagger angle for the leading edge, for which we are able, for every given inlet angle of attack, to find the minimum of losses. So this is the study that has been performed. So for one given stagger angle of the leading edge of the leading blade around the trailing edge, we make a computation of every inlet angle of attack, and we find the losses. And the result is that we're able to find a couple that is a stagger angle of attack, for which we find a minimum of losses versus what we had when we were keeping the stagger angle constant. And this enables us to obtain a very good optimized flow. So here we can see the baseline for an angle of attack of 60 degree and 36 degree. Those are Mach numbers. And when we find the optimized stagger angle, we are able to really decrease the losses and improve the performance. And the goal of this pre-study is that because of that, we will find this locus of point where we have the maximum performance, and we will be able to, in those conditions, extract the particularity of the flow field, and we'll know how to properly mesh those regions to go to LES simulation, where we observe the physics of turbulence, mostly in the region just above the second blade. The second case is a supersonic cascade where the goal is to match experimental data made by VKE. At VKE, they measured one chord axial upstream, the leading edge, and one chord axial downstream. And the goal of Cenaero is to match those measurement points, and then with the LES study what is happening between the blade. But for that, we need to really understand the flow field. That is going to be clearly very complex, and we use SU2. So the objective with SU2 is to be able to find this pressure ratio of 152 for an operating Reynolds number based on inlet condition and the actual code of 1 million. So it's quite a high Reynolds number. The definition of the domain is fairly usual. So we have the supersonic inlet for which we have a given Mach number, a given angle of attack, and we set total pressure and total temperature. However, this inlet condition, the supersonic inlet condition in SU2 is as a weak imposition, and it relies here for that very case on the unique incidence property, which states that for periodic compressor like this, where the actual velocity is subsonic, you have a relationship between the inlet angle of attack and the Mach number, which goes together hand in hand. We set the outlet condition as a static pressure, and obviously we have a periodic condition. We go with a very, very refined 2D mesh. The idea is to be able to really capture the complex flow structure in the field for this 2D simulation, and then to extract those to locally refine our mesh for the LES simulation. And we go with a fairly usual set of steady run simulation with turbulence model SNA. For the convective scheme, we use the GST, and the special gradient I computed with the weight in least square. And as expected, we observe a very complex flow field. So here the geometry is hidden because it's not ours. It's Safran, so you have those very nice black box. um, so we have that very complex flow field with bow shock that propagate upstream, that crosses the periodic boundary, and that going to impinge the inlet. We have a shock-shock interaction when the bow shock is entering with contact with the canal shock, and we have shock boundary layer interaction. So as you can see, the physics is really complex. We also have quite a well-defined wake in here. And so the physics is very complex, and we have phenomena that we'll need to investigate precisely with LES. However, what we so just to be sure, we have a wiper that is super good. So we mostly consistently below 1 for the wipers. And the isentropic number cannot show the value. The CF and CP cannot show either. We can see that they present really distance peaks and maxima, minima that are related to the complex flow field. However, this setting is super sensible, as I was saying, to the unique incidence principle, and we were not able to find when we set an inlet angle of attack. When we measure it at the inlet, we cannot find it again, and we realized unique incidence study. So we took angle of attack ranging from 55 degree to 60 degree and set the Mach number at 1.2017. And on the second case here, we fixed the inlet angle of attack, and we made a computation for different range of Mach number. And what we can see is that the measured angle of attack at the inlet, here it's the inlet length, and here is the measured angle of attack at the inlet, is first of all not constant at all for both cases, and mostly it's constrained between here. I don't think if you can see, but 57.8 and 58.5, and the angle of attack is constrained by the unique incidence principle of this supersonic cascade, and the fact that we are the boundary condition at the inlet that are weakly imposed. So it makes that we are not able to refine to find the condition that the VKE is finding in its experiment. You should know that for this experiment, obviously the cascade is not fully periodic in the experimental setup, and so the unique incidence principle is not, if I may say, as strong. So we find discrepancies between the simulation and the experiment. And so for that, we need to be able to find a configuration for which we obtain the similar pressure ratio as in the experiment. And the solution for that is to make a polar study where we make we take different static pressure at the outlet ranging from 53 kilopascal, 83 kilopascal to 110 kilopascal. And what the variation of the outlet static pressure makes is that the canal shock is going to move from a position near the trailing edge to a position near the leading edge, and we see a decrease in the pressure ratio, and we find the objective pressure ratio at 99 kilopascal, which was not what we were setting at the beginning. And with that, we're able to find the characteristic and the setting for which we are able to match the experiment. And it enables us to extract the position of the flow field, the position of the shock from SU2 with ParaView, and then locally refine our LES mesh. And this is something that will be shown in the future. But right now we're running LES simulation with a mesh that has been designed using that pre-study on SU2, and in the future we will want to compare those results with SU2 and to analyze in more detail the flow field of what is happening between the blades. So thank you for listening, and if you have any question.
Well, thank you for this nice presentation. Are there any questions, Ludovic? So in the first case that we show that you have 3D angle of attack, not angle of attack, but you have 3D these diagrams.
Yes.
You get the best, the least weight, I understand. And then is it like a parametric study or using a drawing of the?
No, that was not iJoint. This was a parameter study where you just script a bash script and you put all the parameters you want and you loop around it. It's exactly.
Yeah, I have one question. First of all, tell you what. Definitely for SU2. I was wondering if you would slide 15 first. For the second place case, if you try this, the boundary link that have lowered the beyond. So activating the non-reflective conversion.
I was not non-reflective boundary condition when not working with supersonic inlet. I was not able to obtain, like, if I do non-reflective condition, I tried that, Riemann, and I don't remember the other one, but I have a Mach number of 0.99 at the inlet, and here the prescribed Mach number is 1.217. So I cannot have that. What would have been great if VKI had given me the experimental setup, then I could have just accelerate the flows to find the same value. But here in my case, I don't have that, so I'm forced to go with the supersonic inlet. And it seems that in SU2 supersonic inlet does not support, or at least the non-reflective condition do not support supersonic velocities.
And this ties into my comment. So when we work on non-reflective multiple conditions like in the case, we never consider this kind of simulations of cases because we're not interested at finding that in this. So we know there is an improvement here in terms really of developing further the boundary conditions, the giant one. So I do see there's an opportunity for you as a scenario to contribute with a small development to a feature that could bring, value to the soul.
That would be interesting
itself. But this is definitely not just the only case in which this boundary condition can be used. There are a number of machine test phases, considering also that nowadays the trend is to look into highly loaded machinery, so really
that's going to come.
Might appear more flexible than machine. So I know that you can share, make available the update, but we can think of creating an artificial one with resemble.
Yeah, I mean the geometry. I think can be, invented without. If the goal is to try just this property here, it's not important if it's not super high performing stuff. But just in the annex, what can be interesting is that, for instance, here it's during the unique incident study, and you have the normal velocity uy, so you see it's almost not perturbed by the flow, but the actual velocity is super perturbed by the flow, and I think the work should be done on implementing condition for which the subsonic actual velocity does not get changed, and so it makes that you can set the problem exactly as you want and not be constrained by the fact that, well, you have no control on the velocity you observe versus the velocity you input into the solver.
Good work.
Thank you.
Any other questions left? If not, well, thanks again.